In today's lecture, we are going to discuss a very important concept of wave motion, and this is actually regarding the combination of tones. Basically, we will learn what is this combinational tones or combination of tones, why it is needed, when it is needed, and what is the basic theory of this combinational tones. Actually, Helmholtz provided a basic theory for the combinational tones. So we will discuss the Helmholtz theory in very detail in today's lecture too. In fact, when you talk about the synthesis of sound or electronic music production, then a combination of tones can refer to the mixing or blending of various audio waveforms such as sine waves, square waves, sawtooth waves, and so on. Actually, these combinations of mixing or blending is for the purpose to create complex sound and text. Okay. So, in simple way, you can say that when two or more tones are mixed together, then we get a complex tone that is called combination of tone. Okay. In fact, why this combination of tone is needed? What is its purpose? Actually, the purpose of mixing or blending of different musical notes or sound frequencies is to create a desired complex and harmonious auditory effect. In fact, in musical instrumentation theory, tones are often referred to as specific pitches or musical notes. The way these tones are combined can vary greatly, resulting in different elements of musical instruments and styles. In fact, there are so many ways by which the tones are combined to produce the desired and pleasant music auditory. And some of the ways by which the tones are combined are called melody, harmony, chords, interval, counterpoint, diatonic scale, pentatonic scale, tritone. Okay, and these are the basic methods, or you can say the basic techniques for producing the combinational tones. But here we will analyze this combination of tones in a mathematical way. If your aim is to explain the combination of tone in a mathematical way, then it can be shown that when two strong notes, let us say of frequencies P and Q, are sounded together, then a series of tones of other frequencies are produced along with the original notes. Actually, there will be a combination of the frequencies. So, in the resulting note or resulting sound, the original superposing frequencies are present, but apart from that, we get so many more frequencies. Actually, these notes are then called combination tones. But one thing here is very remarkable, that you must note that the combination tones are different from harmonics. So never confuse the combination tones by harmonics. In fact, when you talk about the vibration of a string or the vibration of air column in an organ pipe, then you see that there is a fundamental frequency and the overtones appears as a harmonic of the fundamental frequency. But in this case, the situation is not like that. The other frequencies apart from the fundamental are not actually the harmonics of the fundamental frequency. So this combination tones you should definitely not confused with harmonics. Okay. Now if you consider that the two tones of frequencies P and Q get superposed or they are combined, then actually there is so many frequencies produced after the combination. The basic frequency, or you can say the strongest of the combination tone, is called the first difference tone. When you say first difference, that means you will get a tone with frequency which is actually equal to difference of the individual frequencies. As you have considered that P and Q are the frequencies of the two tones which are actually combined, so the difference of P and Q, when you say difference of P and Q, it means either P minus Q or Q minus P. You know, when you find the difference, you always subtract the smaller value from the larger value. So if P is larger, then difference of P and Q will be P minus Q. But if Q is larger, then difference will be Q minus P. So this P minus Q or Q minus P, this is called actually the first difference tone. And in fact, this first difference tone is the strongest of all the combination tones. Okay. But this difference tones is not only of frequency P difference Q, but it may be P difference 2Q, P difference 3Q, P difference 4Q, and many more. Okay. Now it is also possible that if you get a combination frequency P difference Q and another P difference 4Q, P difference 2Q and P difference 4Q, they both are actually combinational frequencies, then it is also possible that our resulting wave will consist of the frequency which will be the difference of these two combinational frequencies. So theoretically we can produce a different tone of frequency which is difference of P difference Q and P difference 4Q, P difference 2Q and P difference 4Q, and this will be 2Q. So theoretically this such a frequency is also possible. Now as in the resulting sound there is the difference frequency, in the similar manner it is also seen that there may be summation tones also present. It means the resulting wave may consist of the frequencies P plus Q, P plus 2Q, P plus 3Q, and so on. Okay. In fact, usually it is the first difference tones, that is P difference Q, okay, or P minus Q or Q minus P, that is easily audible. Okay, first difference tone is easily audible, but the higher different tones and the summation tones are of extremely weak intensity. Okay, so this first difference tone is just you can say this is just like the fundamental frequency. Okay, now we will see the basic theory of this combination of tones, and that basic theory of combination of tones was provided by Helmholtz, and so this is known as Helmholtz theory of combinational tones. Okay. So first of all we will develop this theory, and after that we will see which frequencies actually will be present in the resulting wave, and which are the desired frequency, which is the important frequency. Okay. For developing the Helmholtz theory, let us consider an asymmetric system. And we also consider that the two restoring forces are acting on this system. Uh, and apart from that, the system is acted upon by two external periodic forces. The first external periodic force is F times sine pt, and another is G times sine q2. Here actually P and Q, you know, are the frequencies of the two strong tones acting simultaneously on the system. Then this net force F sine pt plus G sine q2, if you want to write the equation of motion, that will be given by m times d2x by dt square plus mu1x plus mu2x square. Here you know mu1 and mu2 are actually constants. Okay. Now actually just you have seen the strongest combination tone has frequencies either P minus Q or P plus Q, or in P plus 2Q, P plus 3Q, P minus 2Q, and so on. So in general you can say that the combination tone has in general frequencies alpha P plus beta Q, where alpha and beta are integers that may be positive or negative. Okay. Now this equation 1 you can write in this manner. If you take this m in first term of LHS as a common factor, then each term in this equation will be divided by this m. So this equation 1 you can see can be written in this manner: d2x by dt square plus mu1 over m times x plus mu2 over mx square, and that's equal to f over m sine pt plus g over m sine q2. Now let us substitute omega square instead of this mu1 over m. Actually you know mu1 x, this is the restoring force, so this mu1 is actually force constant, and that's why mu1 over m will be is simply equal to a square of the angular frequency, okay, of the system. And we also consider that this mu2 over m is equal to a. We consider it, we take it. And similarly, this f, capital F by m, this is equal to a small f. This quantity small f will have a dimension of acceleration. And g by m, this is denoted by a small g. Okay. Now we will make these substitution in equation 2. Okay. So now equation 2 you can write in this way: d2x by dt square plus omega square x plus ax square equal to this much. Okay. Now from this equation we will obtain the value of x. Value of x, our aim is to obtain. Now how we can obtain the value of x? For this you can see this term which actually introduces the non-linear nature of this equation. So if you talk about the small oscillation, then the term containing x square will be negligibly small. In other manner you can say that this constant a is negligibly small, so this term ax square may be neglected. Okay. And if you neglect this term ax square, then in LHS there will be only two terms, d2x by dt square plus omega square x, and that will be equal to f sine pt plus g sine q2. Now, if you take the operator d dt equivalent to this capital D, then d2 by dt square will be d square. So LHS can be written as d square plus omega square times operated on x. Okay, and therefore x will be given by f over d square plus omega square sine pt plus g over d square plus omega square sine q2. Okay, this has been obtained neglecting x squared term as a being very small. Okay. Now you can see, if you differentiate this force term present in the RHS of the equation 2 times, then when this f sine pt plus g sine q2, if this will be differentiated 2 times with respect to t. So when you will differentiate first time with respect to t, p here and q here will be outside. Okay, so this will be f p cos pt. Okay, and plus g q cos q2. Now again, when you will differentiate it with respect to t, this will be minus p square f sine pt and minus q square g sine q2. So what you are seeing here, actually in this condition, this omega in first term can be recognized by this minus p square, and this omega square in second term can be recognized as minus q square. Okay, so in first term omega square can be replaced by minus p square, and in second term it can be replaced by minus q square. Okay, so the expression for x becomes a small f divided by omega square minus p square sine pt plus a small g over omega square minus q square sine q2. Okay, and as I have told you that we have actually used this capital D equivalent to d dt operator and d square at the place of this d2 by dt square. Okay, oh sorry, not, I have told you wrongly. Actually this d square here I have differentiated 2 times, so d square in first term will be replaced by minus p square, and d square in second term will be replaced by minus q square, not omega but d. I have stated wrongly before this. Okay, so now you can see, when this d square will be replaced by minus p square, here d square will be replaced by minus q square in second term, then expression for x is f over omega square minus p square times sine pt plus g by omega square minus q square sine q2. Okay, now we will substitute this value of x, which you have obtained by assuming this by a to be very small, and so you have neglected the term containing x square. But now after getting the value of x under this condition, we will substitute this value of x in this equation 3. Okay. So in this condition, when you will write the this term ax square in the right hand side, that will be minus ax square. Okay, that will be minus ax square. So you can see here I have written d square plus omega square x, and that is equal to minus a x square. But x is this much, see here. So you can write f over omega square minus p square sine pt plus g over omega square minus q square sine q2 whole square. This is at the place of x, which is defined in this equation 4. And these last two terms in this equation is at each f sine pt plus g sine q2. Now actually we will simplify the RHS of this equation a little bit. So LHS I have written at each, and now let us simplify the RHS. In fact, you can see that this is just a plus b whole square, which will be a square plus b square plus 2ab. So utilizing that very formula, you can write this is first term will be f square by omega square minus p square whole square sine square pt, plus second term is g square over omega square minus q square whole square times sine square q2, and 2 at the place of 2ab there will be 2fg by this much times sine pt sine q2. Okay, and the last two terms are at each. Okay. Now in fact we can write the first three terms or the expression inside this square bracket in this particular manner. Actually I have written it directly, but you can check the algebra by expanding the different terms. This can be written as f square over 2 times omega square minus p square whole square plus g square over 2 times omega square minus q square whole square minus f square over 2 times omega square minus p square whole square cos 2 pt, and minus g square 2 times omega square minus q square whole square cos 2 qt, and plus 2fg over omega square minus p square into omega square minus q square times cos p minus q into t, and minus 2fg over omega square minus p square times omega square minus q square cosine of p plus q times t. Actually when you will expand this cos 2pt, this cos 2qt, this cos p minus q times t, cos p plus q times t, then some terms will be cancelled out and your result will remain like this, and the last two terms are at each. Okay. Now we will operate the operator 1 over d square plus omega square on each term of this equation 5. It means we are going to operate the operator 1 over d square plus omega square on the term in LHS and RHS both. So the expression will remain same. But you can see when you will operate 1 over d square plus omega square on the term in LHS, then in LHS what will remain? Only x will remain. Okay. And when you will operate this operator on the different terms of equation 5 in RHS, then what will be the result? Now you can see. So in LHS you have seen that there will be x, and this is minus a, and after the operation of 1 over d square plus omega square, this will be f square over 2 times omega square minus p square omega square plus g square over 2 times omega square minus q square times omega square, and minus f square this much, and in this way you can see this will be actually the result. Okay, I am not giving the reading, you can note down it this. So this is the resulting equation, or you can say this is the solution of that equation of motion of the asymmetric system actually vibrating under two periodic forces. This is the solution. Now when you will see this equation seriously, then what conclusions we can draw from this? Let us see. The first two terms inside the a square bracket in RHS, you can see actually these first two terms of this equation 6 are constant. Neither sine pt or sine q2 or sine 2 pt, sine 2 q2 is present here. So these first two terms are constant. Actually, this makes vibration an asymmetric one. The vibrations having frequencies 2p, 2q, p minus q and p plus q over and above the frequencies p and q are actually present. You can see there is a frequency 2p here, p minus q here, p plus q here. Okay. So apart from p and q, the other frequencies present in this vibrations is 2p, 2q, p minus q, p plus q and so on. Okay. So in fact, Helmholtz showed that the summation tone of frequency, let's see here, summation tone of frequency p plus q, see here, and the difference tone of frequency p minus q, see here. Actually, Helmholtz showed that the summation tone p plus q and the difference tone p minus q are audible. These two tones are audible. Okay. And from this analysis, you can see that apart from the fundamental frequency, the second harmonics of each component tones and tones of frequencies equal to sum and difference of the component tones and higher order combinational tone are also present here. Okay, although they are extremely weak. Okay. So in this way we can explain the combination of tones by using a Helmholtz theory. Okay. So this is a very important concept, and this will be very useful for your examination. And so watch the video seriously, write down these things in your notebook, revise it, then everything will be clear to you. Okay, thank you very much.